Hello, good morning, good afternoon, and evening. I hope you all are having a great day. Welcome to the webinar. My name is Honnappa. I work at ARM and I serve on the DPDK Tech Board as well. I'm going to be your host. We have three great panelists today with us, and I'm sure we'll have a great discussion about DPDK use cases on hyperscale providers. Next slide, please. Few housekeeping things. The webinar is being recorded. It will end on time, and it will be conducted in accordance with the antitrust guidelines of Linux Foundations. Please place your questions in the comments. We'll take questions and answer them if time permits. Here is the agenda. We'll go through the antitrust policy. I'll introduce the webinar and the goals for today. We'll discuss about the use cases, and if time permits, we'll have the Q&A session at the end. Next slide, please. So DPDK has evolved tremendously since it was open sourced, thanks to Intel. It has a very flexible architecture. It is suitable for deployment on servers, DPUs, and tiny embedded platforms. It supports many architectures today, such as ARM, Longsoon, PowerPC, RISC-V, and obviously x86. It forms the basic building blocks for big-iron routers, firewalls, to your humble Wi-Fi access point. So it's no wonder that DPDK has found use cases in the cloud environment as well. Nathan, next slide. So first up, we have Brian Denton. He's the Senior Program Manager at Microsoft Azure. He will introduce us to Azure host networking and the use cases that he has found in Azure. Brian, take it away.
Yep, thank you. So my name is Brian Denton. As he stated, I'm a technical program manager on Azure host networking team. My primary responsibilities at the moment are working with partners and customers on consuming new drivers that we're introducing with our new hardware coming up this year. And that involves Ethernet, RDMA, and DPDK. So I get to see kind of a unique view of how DPDK is used in Azure, both on by Microsoft and by our partners and customers. So I'll go through first how Azure and Microsoft is using DPDK, and then I'll go through kind of the primary use cases that we're seeing being used from customer perspective in Azure. So next slide, please. So this is a physical diagram of one of our Azure Boost nodes. The kind of key piece here is we've got a PCI Express card that has a system on a chip and our FPGA and our NIC. It's on a single card. One of the kind of goals for cloud providers is to get to a point where the host is just providing resources to VMs. We want all the work done somewhere where it's not going to impact VMs and customers. So we've moved a lot of the control, the routing, and various other host agents that were normally in the host and the hypervisor onto this system on a chip, which is a Linux ARM-based system. So we're trying to get the customer as close to the hardware and as hardware acceleration for I/O and hardware acceleration for our control plane. So in this diagram, we've got basically we're using DPDK in our system on a chip to construct our connection tables. So a packet comes in, it may be a VXLAN, GRE, unpacks it, and we've got a new connection. It'll go through a DPDK application that will add an entry into our connection table to be able to route to a particular VM or back out to the top of rack switch. So this is kind of a high level. We're assuming there's SRIOV with the VMs in this particular case, and that these are virtual functions that the VM guests are interacting directly with. So the reason why we chose DPDK, so going from the host, which has a massive amount of CPU and memory usage, into a system on a chip, we have minimal resources that we didn't have before. So reducing some of the CPU pressure was key. Obviously, performance was a major issue. So we designed DPDK into the system for those reasons. There's some other benefits that going to an application-based solution. It reduces servicing downtime. So restarting an application is much less impactful than restarting Linux. So we went to an application-based solution, and DPDK helps solve that. It also reduces the impact if there's a crash. So a crash in an application is going to be much less impactful than a crash in a kernel. And that also allows us to do updates. So we're continuously doing host side updates on our side, and to be able to update an application versus something that would require a reboot helps reduce that impact and downtime that's needed to service our hosts. Next slide, please. So this is kind of a logical view of things. This is from the customer perspective. I want to kind of set the description here, because this is not unique to Azure. So many of our customers will have multi-cloud and some hybrid of on-prem, and they're trying to get to the point where it doesn't matter where they host their services. So they may have, like, for example, they'll have a Palo Alto firewall, and they want to use Palo Alto firewalls wherever they're deploying their services. Likewise, with the VPN, they may use Cisco for vWAN and VPN to ensure that they've got proper routing between all the various cloud providers and on-prem. And these are all separate products. So the kind of core thing that I want you to get away with for this is that these are multiple VMs here, and every step of the way, you're adding latency and work to each VM and each step. And so DPDK has been critical for these network virtual appliances to reduce that latency and to kind of squeeze out all the performance and get to as close to wire speed as possible. So when you're adding, two or three or more devices in between your client and server, latency starts becoming an issue. So many of these products will use DPDK, especially in a virtualized environment, which has another layer of abstraction to improve performance and ensure the latency is as minimal as possible. So next slide. So in order to test these various network virtual appliances, there's Ixia, and Keysight provides basically packet generation tools to test these various MVA products, and they're heavily used. And kind of the key thing here is Ixia needs to be faster than the device that it's testing, and so they can provide negative testing. They can provide malformed packets. They can do performance testing. It's a test tool, and so this needs to be as fast as possible. And they leverage DPDK to ensure that their appliances can test these high performance devices. So just in general, we're seeing that the vast majority of the usage of DPDK from a customer perspective is through these network virtual appliances of firewalls, routers, load balancers, et cetera. And then with the new generation of Azure Boost, all of the hardware in Microsoft Azure will be leveraging DPDK to ensure that the performance and stability of each VM is maximized. So,
Great.
thank you.
Great. Yep. Thanks a lot, Brian. That was a very good view of how the applications are very close to the hardware using SRIV and VF. So one question for you, Brian. So I know that Microsoft has announced custom silicon platform Cobalt 100 at the end of last year. Can the users expect availability of DPDK on those platforms as well?
Yes, absolutely. So it's a matter of picking the correct drivers, right? So that for Linux, we support DPDK for Linux at the moment. We don't support it for Windows. So the network drivers are part of the kernel. So it's a matter of which kernel you're using. Many of these network virtual appliances have custom kernels. And so this is why I'm working with them, because they have to go through and backport Ethernet and RDMA drivers to be able to leverage DPDK.
Great. Great. Thank you so much, Brian. Next up, we have Rushil Gupta. He's the senior software engineer at Google. Rushil, you want to talk about the use cases you have seen?
Thanks for introducing me. I work as a senior software engineer at Google. We implement the drivers, the network drivers specifically for various stacks, various operating systems like Windows, Linux, FreeBSD, and also user space drivers like DPDK. And we support all sort of customers with various tech stack at GCP. So when we built the DPDK driver, it drew special interest from fintech community, and rightly so, because it is quite a fit, as I'll talk about in my presentation. Next slide, please. So consistency of transaction is the most important thing for these trading platforms. However, it is also difficult to achieve this with high performance. And we are talking about millions of packets per second here, throughput wise, and also while maintaining the low latency. These two tenets are totally are the most important metric for any fintech firm. If a particular transaction is not able to complete in a certain time, they'll lose money, and this is the most important SLO for them. Also, replication of data, persisting it, and replaying it is important for them. So sequencing as well as recovery time objectives and recovery point objectives in the order of millisecond is another important metric for these use cases. Traditional cloud approaches to resilience in fintech, especially, have adopted an architectural approach that makes trade-offs between data consistency and availability. And to meet performance demands, these firms mostly run their entire markets on one or two machines. And that is a high-risk sacrifice for data consistency or availability. And there are outages where data consistency or ordering of transaction were traded for performance, and therefore recovery entails extremely complex reconciliations and costly payouts in compensation to impacted customer, and not to mention the legal, regulatory, and brand impact. Um, in addition, with the whole move to the cloud or the cloud migration effort, uh, it offers convenience of fast provisioning and scalability. Like you can stand up your servers in a matter of minutes in every zone and scale out. But The use of underlying hardware can change at any time. Network interfaces are patched, processes are migrated, you may lose local storage. So providing always on 24/7 services in this context is a hard challenge to solve. Um, and that's where like our networking enters. Google VNIC is one of the pillars of Google's networking on its cloud. It offers best-in-class throughput to support heavy customer workloads, not just for fintech, also for media, real-time data, ML workloads. Um, and DPDK, as we are all here, we know it's able to perform at staggering rate because it does not involve kernel or operating system networking stack. Instead, it offloads packet processing to user space. So when our customers, these fintech firms, came around, they had certain expectations, throughput-wise, latency-wise, and sequencing, recovery time, all those tenets I talk about. So when we provided them, started working on the DPDK framework, we had a good idea that we can beat the kernel driver benchmark. Next slide, please. And as you can see, we did. The latency offered on these systems was 3.5 times faster than BSD sockets, or the kernel driver application. The DPDK application was 3.5 times faster and was able to push 6 times more packets. And I mentioned that these packets were of 288 byte size than the kernel driver benchmark. So we saw gains in both latency and throughput. But I would like to spend more time in this presentation talking about what system actually measured this performance, what system actually was involved in measuring latency and message per second. So next slide, please. In fintech, you can imagine there are various kind of services, and there is massive data to move around with low latency. So that was our use case here. Many core services are broadcasting data to these gateways, and there are servers, as I mentioned, like trading platforms that might be subscribing to to this data. So as you can guess, there is a need for kind of a message passing system, which can move data around with high bandwidth and also low latency while providing all the replication needs. And RabbitMQ and Kafka and there are so many other cloud offerings as well. They are the products that have evolved over time to solve these kind of problems. But there were certain things specific about the customers that we were working with, or the benchmark that we want to beat, that required a very specific message passing system that had these requirements. Um, Publishers will send down messages down to a channel for subscribers to need, and within a channel there are streams that customer can subscribe to, and a channel has to keep messages ordered, and streams cannot block each other, so each stream should be independent. Also, there should be some TCP. There were some TCP like needs to these benchmarks. The loss had to be detected on the both sides and have to be dealt with the minimum impact on latency and throughput. There was a need for flow control and back pressure, so not to overwhelm the clients who are consuming this data. We have to avoid the congestion and make sure that uh, during the process we are not impacting other channels or other independent streams. When congestion occurs, the latencies should be as low as possible, because congestion avoidance or congestion control algorithm can slow you down. So an example, or in mentally you can think about that the message passing system they wanted to build, uh, it might be like a message oriented replacement for TCP with higher level services written on the top. um, so this is an overview of what the need was, and In the next slide, I'll explain how do we what the packet flow looks like and how do we actually measure throughput and latencies. Next slide, please. So there is a measurement client that's sending data and receiving data from an echo receiver. So it's kind of a ping pong model. Both VMs, both of these systems are in different VMs and might as well be in a different availability zones. But in order to benchmark them, we kind of kept them as close as together. But there, for redundancy, we're also keeping them in a different availability zone. Or sorry, the customer was giving them in a different availability zone. So at a NIC level, we have DPDK drivers, which are being, or the poll mode drivers, which are being invoked by the customer's DPDK application. This application is then writing the data to the IPC ring buffer for their measurement app. Now the measurement app is not doing the transmission or receive, but doing more like admin stuff, and it's kind of doing like housekeeping and like setup events for new publication, new subscription, and telling the system what's going on. Also, documenting and measuring all these metrics that we talked about yesterday. Communication happens over media like UDP or UDP multicast, and these senders and receivers are independent agents running in their own threads and doing their own thing. And this allows use of a clean single-threaded code that can go really fast, and that's how they avoid like concurrency and locks by using these IPC ring buffer queues. So a message is sent out, and then echo receiver through the same system sends the message back, and that's how they calculate the latency. And they turn the knob on. They start small by sending a fixed number of packets, but slowly and slowly they ramp up the packets per second metric to make sure that they're able to achieve a certain latency and avoid the packet loss altogether. Next slide, please. So as you can see, this transport layer or the message passing system is the backbone of the whole model. And it is also the backbone of the replication service that is important for the customer. From DPDK point of view, the transport layer is basically where it comes in, and that's where the significance of DPDK poll mode drivers is, and that's where like Google drivers really shine. And we've talked about sequencing and recovery time objectives and recovery point objectives and able to persist data, and this is how it is done. Messages are stored along with header in a persistent log structure, and these logs at a particular cluster follower level, which is another VM, is mapped to disk, but it lives in memory using memory mapped files. These logs are replicated using a protocol of messages, kind of like ping pong messages that we talked about in the packet flow slide. A sender, when it wants to send the message, sends kind of like a setup message to receiver. Receiver can send a status message back that, hey, I have space to archive this data. And the sender starts sending data to receiver. This receiver sends more status messages, kind of like an acknowledgement that I can receive more data, and to this persistent log I can append it, and I have X amount of space left, so you can keep sending. And if those messages are not ACT, they are considered like NACT instead. And in that case, the measurement client knows, or the cluster leader knows that the follower is not active, it cannot receive any more data, and should act accordingly and send data to another backup. So in a nutshell, this is how the whole replication service is working with this message passing system. And the latencies and the PPS we were able to achieve was really revolutionary with DPDK, and doing like 6 million packets per second is something that has really made customers consider DPDK in the fintech tech stack. And that is it. Hope you liked it.
Yeah, Rushil, this is really great. Typically when we think of DPDK, we think of networking application, but here it's getting used in fintech domain. That's really great to hear. So a couple of questions for you. So in the earlier slide, you showed the IPC ring buffer. Now in DPDK, we have a great implementation of ring library. And there are more and more innovations happening in that little library there.
Yeah.
So do you use the ring library for that IPC ring buffer, or is this something else?
So this whole application was developed by a customer, and then they wanted the IPC ring library. Can you go back to the packet flow slide, please? So they wanted the measurement app to be the same, but they wanted to replace DPDK with FreeBSD drivers or FPGA for measurement. So whatever IPC ring buffer library they implemented should be able to perform with all those applications. So I think they rolled their own and did not use what DPDK provides. It would have been faster, I agree, but it wasn't something they wanted to implement because they wanted to try different drivers for comparison.
Right. Yeah, thank you so much, Rushil.
You said you had another question.
Oh, yes, yeah, I forgot about that. So, this is a question about small packets, right? So when I test small packets in the lab, I use 64-byte packets, but you have said it's 288 bytes. I typically end up with PCIe being a big bottleneck. So what kind of performance issues did you see with these small packets?
Yeah, you're right, because this was one of the first clients that I have seen in my tenure here that works with such a small packets. And there's not much you can fit in 64-byte, but 288-byte was just enough for them to squeeze in details of transactions and status messages that I talked about. And yeah, these small packets were able to push the system to the limits, and bottlenecks became much more evident when the constraint was so strict. We had to perform this transaction in a certain amount of time, and we noticed the latency metric to be a bit unstable, and also the performance issues surfaced in the form of packet loss, in ingress packet drops when the generator had too many outstanding packets. Kind of like there was this receive window when increased, we suffered packet loss. So those were the two problems that we encountered. So how we got around it was we asked customer to profile various parts for us, like transmission of subsequent bursts of the packets, the reception of these packets, and the time between packet reception and this measurement app. So we tried to basically measure the metric for each arrow to understand where the bottleneck was. And then how we solved it, that we found a few bottlenecks in the measurement app and also in the drivers. In the driver level, we were ringing the doorbell too often. So we suggested, or we implemented better strategies for batching at both driver level and at the batching requests that are being passed to the DPDK receiver, to the application thread. So application has better opportunities to prefetch and amortize. Yeah, batching was one of those approaches that we use to solve this overwhelming or bottlenecks at every level. Given the high cost of synchronization, it's also a good idea to introduce some coalescing in the system. Make sure that each packet is at least X microsecond apart. And this is again coming back to the batching idea. So that was in one single word, that's how I would explain that we solved this bottleneck problem. And once implemented at each level, we were able to go from we were essentially able to 2x our PPS, and we were not seeing those unstable latencies anymore. The latencies were very predictable for the benchmark. I hope I answered your question.
Yes, yeah, it was very clear. Yeah, thank you so much, Rochelle, for introducing this use case. Next up, we have Jim Thompson. He's the co-founder at Netgate. Jim, do you want to introduce your use case?
Sure. Jim Thompson, like the slide says, I'm a co-founder here, co-owner. I run the engineering part of the company. You may know Netgate for a software product we do called pfSense, but today I'm here talking about Tensor because we don't use DPDK and pfSense. Next slide. So the most common use case in cloud, of course, is to stand a set of applications and take incoming, TLS encrypted HTTP requests. But there are also use cases for a customer having an on-premise network or more than one data center, and also wanting connectivity into a cloud region via that, either for back-end applications or enterprise applications, or even for administrative activities. So here's the most common use case for that, where you have a VPN connection between a on-premise network, could be a branch office, could be a headquarters, could even be someone's home network if they work from home, into a VPC. And Amazon and Azure and Google all support the idea of a virtual private gateway where they will terminate an IPsec connection for you. Next slide. And then there's a bit more sort of complex version of this, essentially the same thing, where you have more than one VPC all connected into a transit gateway. So there could be inter-VPC communication, and you still want to be able to maintain this, secure private communication out of an on-prem network into that architecture. Next slide. So there are, like I said, both Amazon and Azure offer, connectivity or termination for IPsec tunnels for these use cases, but they come with some limitations. The per tunnel bandwidth limitation on AWS is 1.25 gigabits per second, and also 140,000 packets per second. The normal way to overcome this is to use multiple tunnels with equal cost multipath. So you could say put 4 tunnels together and get 5 gigabits, but your single flows are still limited to the per tunnel bandwidth, and you can't use any static routing. You have to use BGP for that. Additionally, you can only have 5 VPN private gateways per region, or 5 site-to-site tunnels per, and then you can only have 10 tunnels per gateway. So that's total of 50 tunnels per VPN gateway. And there are a number of other limitations on given a URL there. It's pretty easy URL to find if you just search for it. There are similar limitations on Azure. The Gen 1 VPN gateways, again, 1.25 gigabits aggregate through the VPN gateway, and a limit of 30 tunnels. And then they improve things quite a bit with Gen 2, where you can do 10 gig aggregate and 100 tunnels. But these things can, you can quickly scale past this for some large organizations. So next slide, sorry. So Tensor is a vRouter. We use a VPP/DPDK data plane with all the normal CLI and REST-conf interfaces into the operation side, as well as IPv2 and BGP and OP, all the normal things you'd expect from a vRouter. And the data plane supports a lot of tunneling protocols: GRE, VXLAN, IPsec, which we're here to talk about today, WireGuard, which is a fairly new VPN protocol, crosswires, etc. And we use the DPDK pull mode drivers for NIC and cryptography offload. And using DPDK, we preserve very high throughput and low latency. And you've heard the other presenters talk about that. But even almost more importantly, it simplifies supporting for us. We have a common interface into the NIC driver on these different platforms, and we just include the driver. There's actually more work in packaging for the different cloud platforms than there is in establishing connectivity with a NIC. And so, in terms of performance, we recently measured 37 gigabits per second using ASGCM for IPsec. That's on a fairly recent Sapphire Rapids. And I want to emphasize that's using one core, the Sapphire Rapids. That's not using the whole, 54 cores that are on the chip. That's a per stream software-only cryptography benchmark. And WireGuard runs just a little bit less than half of that. Or if you run Cha-Cha Poly and IPsec, it's almost exactly the same benchmark as the WireGuard throughputs. And this will scale with, additional cores or streams or, some kind of hardware offloads. So there are, hardware offloads available in some of the cloud providers now for cryptography. But this benchmark is really just using just the CPU instructions. Next slide. So the net of it here is, there are instances on these cloud providers that scale to 100 to 200 gigabits total throughput. So you can use one or two VPN concentrators and really, terminate the entire enterprise IPsec traffic inside one of these VPCs, and then also have additional connectivity out to the individual VPCs for individual apps, or even the forbidden use case, which is cloud to cloud, even between different providers. I think that's it for mine. I think the next slide is somebody else's.
Yep. Thanks a lot, Jim. It's good to learn how DPDK, allows software vendors to port their application easily from cloud to cloud. I think that's a great takeaway from your presentation here. Now, what kind of packet sizes do you see on the VPN side? Typically, I hear that for IPsec use cases, it's large packets, 1,500 byte-size packets. But what have you seen for your application?
We actually measure also with 64s, but those benchmarks tend not to be interesting. The common use case is moving bulk data over the VPN connection. You're trying to get new images or data in and out of the remote VPC, that kind of thing. So we measure IMIX and 64s and 1500s, just like everybody else. But the VPN normally is constrained by the speed of the encryption.
Yes.
If we take the encryption off, we just fill up the interface almost no matter what.
Okay, great. So now going back to that portability between the cloud environments, how was your experience? Can you talk a bit about that? Was it very smooth, like I said, or were there issues that we need to look at in DPDK?
Early on, there was a bit of difference between the various cloud providers and their NIC support for DPDK, but recently, it's almost a non-event. We literally just, bundle in the NIC driver, the DPDK NIC driver for these various platforms, and just, instantiate it at runtime. Like I said, there's almost more work now in packaging or making sure that the version of Linux we're using is compatible with that DPDK driver than there is in any kind of tweaking or tuning with the actual driver itself.
Okay, great. That's really good to see how DPDK has progressed on this front. Now, just to add to that, in the community, we have an effort going on to stand up a testing framework where we would be testing all the PMDs against that standard set of test cases that we would develop. So I think that would also ensure that there's feature parity across all these PMDs. Good. Thanks a lot, Jim. Thanks a lot for your presentation. So just to summarize our discussion, what are DPDK's advantages in cloud environments, right? So obviously, it's high throughput, low latency. DPDK is very well known for that. Today we discovered it provides great portability across different cloud environments. And we learned that it's not just for networking applications. That's great to hear. So now, we see cloud providers creating their custom silicon platforms. DPDK obviously now supports a lot of CPU architectures. So with the proliferation of these CPU architectures in the cloud, DPDK is ready. DPDK is ready to support these custom platforms. Good. So with this, we come to the end of our discussion. Now we'll take some questions. I have a few interesting questions that have come up. The first question is live migration. So how do these platforms support live migration with SRIOV? Maybe Brian, you want to go first on this?
Yeah, so I'm assuming this is a specific to Azure question.
I kind of feel it's not very specific, but maybe we'll start with you. We'll go to Rushil.
I mean, so essentially we will bind and unbind an interface. So we're kind of in a transitionary period right now where we have our old synthetic data path, the old path that goes through the hypervisor, that goes through the host side, and we call it synthetic path, in addition to our SRIOV data path. So right now there is a benefit of that, because when we take down the VF interface, for example, the traffic will automatically get routed through the synthetic software path. So you never lose connection when we service a virtual function right now. But typically when we do live migration, processes will take down a node and move your VM to another physical node and reallocate it and rerun it, right? So there's a blackout period of when that happens. But typically from the perspective of DPDK applications, they'll see the virtual function get revoked. And then when it lands on the other side, it comes back up, it reattaches. It's up to the DPDK application to ensure that they're reattaching to that VF. But we use the NetVSC driver, which is to our VM bus, which is the synthetic path, to help handle that transition.
Thank you. Rushil, have you come across any live migration use cases?
No, I'm not aware of how if they have any specific implementation for SRIOV, but it's pretty much what, similar to Microsoft. There is a blackout period, and then we have to attach and reattach this SRIOV driver, these VFs, and then it's up to a DPDK application to use those virtual functions. But that's all the knowledge that I have in that matter.
Okay. Yeah. I think live migration is a complex use case. It's just not about the PMD. There's a application on the top. You need to take care of how that state is carried forward and things.
And I think in general, it's just as long as the Linux provides hot plug capabilities on PCI devices. So as long as we have drivers that can support that, we're leveraging Linux for that. We're not doing anything special.
Okay. Jim, have you, as a software provider on the cloud, what have you seen? What's your experience with live migration?
It's an interesting, application use case where you want, your applications to move, but it's not something we really support or even investigate on the router.
Okay. Great. So now moving on, Brian, I think this is a question specifically for you. So you showed us how different network services are chained together.
Yes.
So the question that has come up is, why do we have to create those individual services? Why not put all of them together in a single VM?
So I think ultimately that's often the goal, right? From a customer perspective, is to try and combine those services as much as possible. Many of those products, so like a firewall is typically going to have both the network firewall and WAF functionality, for example. So you may not need this separate VMs for that. But all of these network virtual appliance products are full VM images that take control of the network interfaces and plug them directly into their packet processing engine. So you can't take a big IP and a Palo Alto and put them on the same VM. They're not applications, they're full systems. And they're designed that way. So if you can get away with combining them or having, less using a load balancer from Azure versus using a big IP, or, many of the especially the large customers are very standardized on what products they use. So if they're using Checkpoint or Palo Alto for a firewall, they want to use that everywhere. And you can't just combine that with a big IP or a VPN endpoint from Netgate or Cisco. So typically they're forced partly from policy, but also these are very dedicated products that require a full VM. And so it just naturally, you would have to do multiple VMs to get all that functionality in place. And so some of them do provide containerized versions of some of their functionality. So that can be an option. There's some extra hoops of, unbinding and binding interfaces through a container, but most of those MVA products that are using DPDK in Azure are full VMs.
Yeah, so I guess there's some amount of, hey, I'm familiar with this.
Yes.
With this VM for this service, so I'm going to use that versus some other VM for something else.
Because you don't want to, use Palo Alto for on-prem and then use another firewall for Azure, or you want to use the same infrastructure everywhere, and they typically try to standardize on that, which inherently forces multiple VMs.
Sure, thank you. Rushil, I think this question is for you. So in fintech use cases at GCP, what kind of networking stack have you seen? Do they require TCP, UDP, or Quick that runs on top of DPDK?
As I mentioned, they kind of rolled their own, but it was written on top of UDP. This wanted some TCP-like capabilities, like flow control and congestion control and detection of loss. But they didn't want to use it because I think the libraries that DPDK provides for TCP were quite new and they were not well versed in it. And B, that stack, even for kernel drivers, comes with a bit of overhead. They understood that latencies need to be as low as possible, and congestion control algorithm might slow them down. So they ended up writing their own over top of UDP.
Okay. So latency requirements are so tight that they want to control every bit of that stack.
Yeah.
Okay.
Yes. Yeah, there is a nice talk about this, like why they chose this, and I think it's available for free. Yeah.
Great. Yeah. There's a discussion that has been going on for some time in the DPDK community about trying to come up with a TCP stack that is native to DPDK. So looks like, if the DPDK community has to provide something like that, which is native, I think there are very good use cases.
Yes, for sure, as we saw with this customer.
Okay, great. Okay, great. Yeah, a question for you, Jim. So we talked about containers and VMs. So what does your customers want? Do they want your router in a VM, or do they prefer containers? And containers is like typically I grew up with VMs and then moved on to containers. Maybe containers is the latest thing that's out there. So what do you see in your experience?
What we see is more VMs, honestly, than containers. There is some effort internally about supporting some of the, specific cases for container networking. So being able to terminate VPN into, say, a pod, and then be able to support privacy into the pod, but that would still be, if you will, overall on the VM. So that tends to be our focus.
Okay, great, thank you. Great, so these are all the questions we got from the users. Yeah, thank you so much for attending this webinar. Thanks a lot, Brian, Jim, Rushil. I know this is additional work on top of what you are doing in your day-to-day life. Thank you so much for being patient with me in terms of the changes that I asked for the slides. And there's a lot of effort from others behind the scene as well. Thanks a lot to Nathan, Ben, Thomas, Timo Driscoll from Intel to guide us in terms of, hey, what is the right direction for this webinar? Yeah, thank you so much. I think it was a great discussion. I hope the users got some new information out of this. Yeah, thank you so much, and we'll call it a day here.
Thank you.
Thanks.
Thank you.